So anyway, we're gonna do chapter 10. We have main here, which will just say pure unit. So should be good enough. This anymore. We need some buffer space here so that I don't cut off my typing, which I accidentally did last time. And we'll just watch down there. That. All right. When we look back at recursive recursive functions we wrote, there's some common features that we may notice. First is that many times we pass state to our recursive call. So here's that state, and then list. So depending on the value of this thing, then we do stuff. Okay. Yep. When we recurse, we add 1 to the current index and pass it to go. We also short circuit. The above example. Yep, short circuit when we find what we're looking for, which was nil. We'll terminate the recursion. Oh, or if we find x. Yeah, this is like find index. Okay. Yeah, and then this one always exhausts. Great. Okay. Let's start with length. Not tail recursive. We talked about that previously, if I recall correctly. We have no state to pass here. The state is maintained in the stack. We need to return to add 1 count. In the tail recursive version of length, explicitly pass state, which is evidenced by the existence of a go function. Yep. These types of functions are perfect for a process called fold. Fold is a generalized way to iterate with state. Major limitation of folds is they do not short circuit. This means that we can rewrite length using fold, but not index or find index. Okay. Fold by other names. Fold is also called reduce. In our case, our length function, we reduce. In category theory, you'll hear the term catamorphism, breakdown structure. This is opposed to an anamorphism, to build up structure. The point here is that folds are called catamorphisms because they break down the original structures. There's another concept called unfold, which are used far less often and are called anamorphisms. Cool. All right, so here we go. Foldable type class. In Purescript, a type can be foldable if it has an instance of foldable. Here's the type class. So we have ABB, BAB, BFAB. Okay. Yep. These are pretty classic definitions. Fold map is another pretty classic definition. Just give me a foldable of A and some way to convert those A's to a monoid. Then we'll just combine them all. The reason that monoid is required and not semigroup is because if FA is empty, we need to return empty. Okay. Function to process the foldable element with its accumulator. So the A is an accumulator, the B is the element, and we need to be able to return a B. Fold L is exactly the same, except that the accumulator is from on the right side. Yep. Fold map, sort of already discussed. Yep. That. Okay, so fold R is right associative and fold L is left associative. Yeah, so there's the accumulator in a fold R. it's applied to the leftmost element first, and then, or sorry, the rightmost element first, leftmost, and then the fold L left associative. Mm-hmm. Yeah, so this is just the shorthand notation. Hmm. Okay, cool. Remember flip swaps first two parameters. Yep. Foldable for list. Let's look at the details for the implement. Foldable for list. Definition. Yep. So again, these names are not required anymore. What we've been putting in place of question in other type classes is the type with all its parameters. In other words, or sorry, for example, list A or maybe A, as in this. Um, mm-hmm. The type parameter to each class is A, and its kind is type. Yes, wonderful kinds. Types categorize values in the same way as kinds categorize types. A value has a type, and a type has a kind. In other words, the type of a value is called type, whereas the type of a type is called a kind. Huh? The type parameter to the foldable class is f, and when we look at how f is used in type signatures of the methods, we'll see that f takes another type. That means f's kind is typed type. In other words, f is a type constructor. Just like data constructors. Yep. So just left and right are all data constructors. And then the kind signatures for maybe are we take a type to return a type, either takes two types to return a type. So the instance here is a foldable list, which is type to type. Cool. Not replace it either, but we could not replace it with either since its kind signature is type to type to type. Instead, we would have to fix the first parameter and replace f, either A. Yep. Okay. Now on to writing fold R. First, the base case. So if we get nil, it's just the accumulator. And then have this to fold. Yep. Mm-hmm. With D. Yep. Right. L. So I've seen this definition before. Um, so this isn't particularly scary to me, but kind of scary to you. No. But yeah, I mean, basically the same thing. Like this. Okay. We pass our new state to the recursive call. Return our new state from the recursive call. Okay. It's important to let this take a minute to let this sink in. in functional programming, we can only pass in state changes and return state changes. It's going to be a concept we revisit when we look at the state monad. Now we're ready to write fold map. Yep, so this is the base case, and then have the recursive call. There are two possible approaches we can take when filling in question. We really wish this was just a whole. Dude, is that like a thing in Purescript that I'm just not aware of? Or do holes not work the way I think they work? Unknown value. What does this one say? Unable to parse. Okay, so yeah, it seems like they are treated slightly differently and both not really the way you maybe want them to. Yeah, this just says unknown value. Holes are so helpful. I wonder if that's coming to the language. Okay, so we can either fold map from the left or fold map from the right. In the Purescript library, there are two functions, fold map default R and fold map default L, which effectively is the above code. As it turns out, the authors of array foldable type class chose to be right associative, while the authors of list chose to be left associative. While this is unfortunate, it's possible to convert between a list and an array, so we can choose which one we want. We also can explicitly call fold map default R on lists, but these non-default solutions cannot benefit from type classes. So we'll pick a left associative one. So I think the left associative one is the one that's used in Haskell as well. And I think that the left associative one can work on infinite lists. So I think that's why that's chosen. Maybe I'm recalling incorrectly. Not sure. Okay. So anyway, there you go. Rewriting length with folds. Since fold L and fold R pass state, we can recode the tail recursive version of length using fold. We can just write that real quick. So length is gonna say for all A, list A, int. We'll just call this length F. F is for fold. There's no reason for us to call it F. So we're gonna have a function here, which is gonna take our accumulator and our value, but this way because it's a fold R. And then we need to do something here. We're just gonna say ac plus 1 because we don't actually care what this is. We need our identity element for summation, which is 0, and then that's it because this is right. So we need to spago install lists. And then are we good, or do we have to include data list as well? I guess not. Okay. Does this really build? I'm now confused. Should I just wait for this to finish? I'm just kind of surprised that I don't have to import something. I assume I need to import data list. Yeah, there it is. Okay. So import data list. We should only need that. This should come from 1. And then we should be good. Wait, we don't need list? I'm confused. So it's like it's there, but it's not there. I'm confused. Anyway, that's fine. So we could write this with foldr. Um, Another option is you could say you can use the monoid instance. So a monoid a list a int, I think. Oh no, you don't even need that. You don't even need this to be a monoid. This doesn't matter. Um, oh no, because you can't use. Never mind. I was thinking that you could use fold map, but you can't because fold map requires the thing to be a monoid. So you'd have to first zip it with um like an increasing, or no, you could just zip it with an infinite list of ones and then sum the ones. Something like that if you wanted to. Um it would be sort of a weird thing to do, I think, but you could do it. Okay. So yeah, use fold L or fold R. I just picked fold R arbitrarily. If you're doing this in Haskell, I would pick fold L prime, but I don't think it matters in this particular case because of the semantics of Purescript. Maybe that's wrong. Um, Compare the implementation of fold R and fold L to see if you see a reason to use one over the other. I really don't. I certainly can't do this. See if one is more efficient than the other. Here's a typo. I should write this down. Page 3. Fold R. Okay. Um. Okay. Apparently, this is tail recursive. I don't immediately see why. But I guess this kind of does look like I'm building up a stack. Um. Oh. Okay. We ignore it with underscore. Yep. All right. We'll just move right on to chapter 11, I guess. Um. Chapter 11. Okay. We're probably going to want list. Yep. Spago install lists. All right. So, I don't know what we're going to mess with here. Just a reminder that we're going to be overriding things from Prelude, so we need to be very explicit about what we bring in. So, unit, pure, unit, show. So this operator here is an isomorphism. It's denoting an isomorphism. So we have that. We're gonna need data list, and cons. And we may want log, but probably not. We'll probably just code things up and do it in the REPL. So I think we're going to be writing this reverse function. Is the plan? Yep, we did that. Here's the code we initially wrote for reverse. Go ahead and rewrite this using fold L or fold R, whichever makes the most sense. Then continue reading. So I'm pretty sure it ends up being fold L. So this is list. So this is basically just list A, normal arrow, list A. It's just like a shorter way to write that. And you also don't need the for all. So if you didn't have this, you would have to write for all A, list A, and then a regular arrow, and then list A. So you can remove all of that by having the isomorphism arrow. Okay, so if I recall correctly, this is fold L, cons, empty list. We may be required to use mempty here, or nil. Might be nil, and I think this should compile. 1. So you have what? Oh, 1 second. Pursuit doesn't know what I mean, obviously. Okay, I just need to pin my screens here. How's everybody doing this morning? Been a little quiet, which is obviously fine. There we go. S list. Yeah, so nil. And if we look here, we should have the cons operator somewhere. There it is. What am I doing wrong here? Build succeeded. I don't understand. Oh, because I'm in the wrong chapter. There we go. Okay. So we want Yeah, so I was doing it backwards. So is this right though? So this needs to fold from the left. So the accumulator will hit the first element first and then put it against the accumulator, which is exactly what we want because we want the first element last. I'm pretty sure that this is right. We can just quickly log it. Um, oh, I can't do it like that, I don't think. I have to do like 1, 2, 3, nil. Should work, I think. 4 and 2. Yeah. Okay. Vago run. This is why this ends up being frustrating because like I have this thing and yeah, so there it is reversed. You should be able to see it on the screen. 3, 2, 1. So if you use fold R, that will do nothing, if I recall correctly, because now we're taking the furthest element in the list and sticking that on the accumulator first. So we're just gonna get the we're gonna get the exact same thing that we just like. This is basically an identity operation. Yep. So you need to use fold L, otherwise this doesn't work. Which hopefully should make sense if you think about it, or like visualize what's happening. What operation happens first? The first operation is the first element gets prepended to the list. Okay. Yep. Okay. So max. Um. So max is takes 2 values and returns the maximum. Okay. So I don't understand why I need folds here. So yeah, this is kind of like a non-classical fold problem. So we need. I don't really understand. Like, if you have something that's orderable, 3. So if you have something that's orderable, then you just do this. So I don't really understand what the question is asking and what this has to do with fold. But that would be max for this definition, if I understand correctly. So if we log log show is effect unit log show equals I think that this should just work. Yeah. So I'm a little confused by why this is here. Oh, okay. That's why. I guess that's fine. I guess I should have anticipated that, but whatever. Okay, so this is gonna be ord a list a. Actually, it's really not gonna be list. It's gonna be uh foldable a. You can't do that. Right. Then we're gonna get a list of a, and we're gonna produce an a. Actually, we're gonna produce a maybe a, aren't we? This needs to have. So this is the thing to show. Okay. List is foldable, so we don't need to say that. We do need orderable, and we need an a. List of a and a. Okay. So this is like our empty element. This is our list. And then we're going to fold our, well, I guess we'll just use fold L. We'll have an accumulator and an X. And then we're just going to say max. Actually, this is just max. Doesn't matter. And then we're going to pass empty. Actually, it's just fold L max. I don't need to write anything more than that because I'm just going to pass these elements back into max. So it should just be that. Do improved code. I don't know why I would write this without a fold. Using fold. And then yeah, so if you had a non-empty list, then you wouldn't have this problem. So note a non-empty list doesn't require a parameter. Okay, let's see if we can empty. Okay, and then we need to bring in Spago install non-empty build. And down here, we need to bring in data non-empty, non-empty. And we want the const operator for non-empty. Okay. But really, that's probably not what we're looking for. I would guess that there's just a fold operation in here that we can just like use. What am I supposed to be doing here? What's the goal? I'm supposed to be writing. Oh yeah, okay. So we could write this as well. And we don't need to write L here. We could easily just use the rest of the list. We've already lopped off the front, so um I think they want me to write. I don't know. I guess what we could do is do the following. So we could write non-empty and then x xs, and then this is literally just find max xxs, I think. Hey Himar, how's it going? Why do all Purescript functions have the for all keyword? Because Purescript uses the scoped type variables plugin basically everywhere. So that's the way of like proving that you need an A, or not proving. I don't think that's the right term. It's like saying all A's in this definition are A. For what it's worth, it seems like you might be able to remove it, but maybe there's like a trick that I can't think of offhand of why you can't get rid of it. I'm not 100% sure. What is this complaining about? Yeah. It's like if you use scoped type variables, you're gonna use for all. Um, and then yeah, for things like that, you need it as well because you need to like delay the decision on what A is, right? It's like you use it when you want the caller to decide what A is, if I recall correctly. I might not. Um, so what is this complaining about? I don't understand. That's the way I try to think about it. Is like if oh this is a list. That's why. So we want non-data list types non-empty list. That's usually the way I try to think about it is if I need the caller if I'm in Haskell. I suppose it's true in Purescript as well. If I need the caller to determine the type of A, I usually want a for all. So actually, if I just put list here, is it fine? Ah, okay. So there's like, so what, how do I like get at a non-empty? I actually want to just get rid of this because I would like to just use these if I can. So it should be non-empty list A like this. And then how do I actually use this thing? Non-empty. So the right side should, oh, okay. So the right side should just be a list. And then the first element is just, it's just like this. If we wanted to construct a non-empty list, we could use this, but we don't really need to because find max non-empty is just this. Or we could also write, instead of find max, you can just literally write fold L max XXS. And then you're good to go. I guess. Yeah, see, like this is more work. Like, why would I do more work if I don't have to? Okay, so writing find max not empty using fold L1. When you know your collection will never be empty, you also know that you'll always have at least one element to pull from that collection. In our case, we have a non-empty list, and we use pattern matching to pull out first. Yep. We then passed first to fold L, but this work is going to be the same. This work, and there's a helper function called fold L1 that does some of the heavy lifting. Notice there's no initial state. Fold L1 gets its initial state from the head of the non-empty collection. Yeah, we don't have a B in this case, which makes sense. Yeah, okay, cool. Fold L1, sure. Yep, we no longer need to pattern match out this thing because we have fold L1. So like our implementation here doesn't actually work in this case. We would, if we wanted to use fold L1, we would have to write in this notation, which is going to look a little strange, but uh, use semi-group foldable fold L1. Okay, where'd fold L1 go? So let's delete this, get this to fail again, and then get 2. So yeah, we could do this like this, or do it how they have it, where you have the non-empty list thing, and then you just get the non-empty. Oh, well, I guess you can. What does this thing take? This thing takes probably a non-empty list, which is the trick. Can we literally just write this? Is this legal? Looks like it. So you don't even have to do that. Cool. All right. Writing fold L1. Fold L1 should make fold L1 sure made our work. I just can't read. It could seem like a lot of magic that is right up to the point that you write it yourself. Okay, so fold L1 prime is just gonna be it's gonna take a function A to A to A. It's going to take a non-empty FA. And it's going to return an A, I guess. So we have F. We have a non-empty X XS, and we just say fold L F X XS, probably. Ah, right. So F needs to be foldable. Foldable F. Otherwise, we can't use fold. So that would probably be my guess of how to implement that. So it's like one parameter less, which is fine. Okay. Yep. Or this. I keep forgetting about this notation because you can pattern match using it, but anyway, not a big deal. Cool. Writing sum. Okay. What time is it? 8:30. Nice. Okay, so we're gonna take list int, and we're gonna return an int. This is gonna be fold L. This should come from semigroup. Or prelude, I suppose. Why did it do that? Mempty should come from monoid, but also prelude. What the heck is it doing? Ah, right. So, hey, yappy yappy. How's it going? Probably like this. I am doing swell. Okay, fine. I won't do this. Just oh, duh. What is that? Why is it doing that? It's so strange. I don't really understand why it's doing that. Okay. Cool. Some super easy. I don't know why we're writing the recursive versions anymore. It seems like we can just skip the recursive versions if we know what folds are. Okay. Yeah, that will fail. So basically anything that implements the plus needs to be a semi ring, if I recall correctly. I also can't remember if this is like this. I think it is. And then we can say A to A. Actually, I think it needs to be a group because we need to get the 0. So I think it should be group, and then that way we can write whatever the 0 is here or something. Oh, yeah. Good call. So we can say semi ring and then monoid, and then this can just be empty. This needs to be, wait, that's right. 2. Okay, and then we need semi ring, which is 7. There we go. Cool. Nice. Good catch. Yeah, I can't remember exactly which operators the group adds, but one of them defines a 0. I just don't remember which one. Well, maybe it's just that you would just use monoid. Maybe that's in Haskell that we get it a 0 or something. Or I'm thinking about something completely different. Okay. So I think that should work. Yep. Compiler error. Oh, it does have a 0. So I don't even need monoid. It's probably just empty. So maybe we can just do this. 7. Look at this. I don't understand why it's doing that. It wasn't doing that like literally yesterday. I would guess that this is literally just implemented as empty. We can go look. Semi ring source. Yep. It's interesting to me that it's not just implemented in terms of monoid, but it's probably because there are things that are that I don't understand. Or because it's simple enough to just say put a 0 here. I knew I was pretty sure that I recalled that, so that's kind of nice. Wait, I don't understand what you're. Okay, so a monoid is the mempty, which so actually that's a why. Actually, okay, so this was kind of a weird thing. So if we write monoid here, it's wait, what? Okay. So okay, hang on. This is actually kind of confusing. This is not the code we want, right? Because well, it is actually, but it's a little weird because if you wanted to use int, you would have to use sum a to get the right mempty. So like while this code is correct, it's not like what you actually want. What you actually want is this. Because how would it pick which monoid to use? Yes, exactly. So semi-ring is, yep, that's a better way of saying it. It's both the addition and multiplication monoid in one type class. So it knows when to pick 0 and it knows when to pick 1. Well, it doesn't know. I mean, you have to tell it, but I would guess that anything that's a foldable semi-ring would just do this. Okay, cool. That's pretty sweet. I'm glad we figured that out because I'm glad you asked that question as well because we thought about it more and it makes sense. It's kind of weird that you would write monoid there. Wouldn't know which one to pick. All right, let's keep going. What do you want to, or what are you confused about? I guess so. Semigroup defines this. So semigroup is this, and monoid. Oh, I see. Okay, I understand what you're saying. You weren't confusing semigroup. You were just like accidentally conflating the two things. Okay. Here we go. Yeah, we could generalize this a little bit more over foldable as well. Cool. We didn't do that, but it is what it is. But if we do have this, then we can write like more interesting things. Oh, foldable. It's a fair point that I didn't think about very carefully. So if we have a tree, yes, folds over trees. I should really work more with trees, honestly. How do I write deriving? I don't remember. Which is pretty hilarious, actually. You really have to write it separate? Instance. This gets me every time. I just don't write Purescript enough to remember this. Okay. And then this needs to be tree A. Tree A. And then we need eq. And then this needs to say show a like this, I think. And then I swear I did this like a little bit ago. Oh, I have to do it with generics. Because why would I not? and then this is tree like this. Okay, so we need generics, which come from here. Okay, and then this is probably show A, tree A, like this, but I probably also need for all A. Maybe I don't need that. Maybe I need it here as well. E okay. Easy Pete's. Um okay, so now we can show trees and check if they're equal to each other. Which we probably want. Um mm-hmm. Okay. All we have to do is make our tree foldable. Easier said than done, though. There are a number of things we must first decide before we make it foldable. Are we going to favor the left side or the right side when we encounter a node? Are we going to traverse the tree depth first or breadth? This breadth? It's breadth first, isn't it? Okay. Pretty sure that that's a typo. So this is page 375. 5. Breadth first. Okay. We didn't have to make these decisions for lists since there's only one way to traverse a list from head to tail. I guess you could traverse it backwards if you wanted to. But a tree structure that can be a tree structure. A tree is a structure that can be traversed in a few different ways. I can't type. To make our code easier, let's make an executive decision and choose depth first. Oftentimes, it's worth stopping and creating a simple example of your data structure to help you develop your code. Here's a simple tree. Hello, tree. So, simple tree is a tree of int. Simple tree. Okay, so step one, we have a node, and we have a left subtree that's a node, and a left subtree that's a leaf 5. In the right subtree, we have a node. The left subtree has a leaf of -1 and a leaf lead. Leaf 14. And that's that and that. And then this right subtree has a leaf of 99. I think that should compile. The left subtree, right subtree, right subtree. Okay, I think it's right. Yeah, so addition is associative, so it's not a problem. Okay, so we're just going to favor the left. Okay, let's see if we can write foldable. Instance foldable tree. I don't exactly remember what we need to implement, so let's just look at pursuit s foldable. I think we just need to implement fold R and fold L and fold map. Some combinations. Okay. So we need to say fold R, which is going to get a function, a tree, and like an accumulator. Is that the right order? I think it is. Fold R. Uh, accumulator comes first. Okay. So now we do need to write the recursive part because, you know, you have to. So we first have our leaf, which would be this. And so we're just gonna take F ac A. Like so. And then we're gonna say so F takes this second. Let's make this X because I always make it X. Okay, so we favor the left, I guess, which means we do the left first. So we need to fold um what do you mean? Oh, sure. And then we need to switch the order. So leaf what's fold map again? Forget. We have A to M. So we only have an F and this. So all we can do is do F of X. How do we combine them though? Oh, well, we're going to combine them later because they have to be monoids. So then we're going to get a node left and right. If I just put this here to, okay, that's the only thing that complains. And then here's where we need to combine things using the monoid. So we're going to fold map FL. Is this it? It feels wrong. But basically, we're just getting to our leaves, right? So we get to all of our leaves, apply X, and then just combine them all together. Feel like this is right? I would need to write some tests to make sure it's right. But I'm pretty sure that this favors the left tree over the right tree by doing this. And then I don't know, I think this is right. Why would I do this? Wouldn't I write the foldable instance first? Oof. Tough. Okay. Why would I convert these things to a list? I'm very confused by this code. Yeah, like, okay, so if I don't know the fusion rules, so like, it's possible that it can do this in like one pass, but maybe I'm like thinking too Haskell-y. But I feel like this implementation, I mean, this is very similar to the list implementation, but I'm not convinced that we don't traverse the list twice here. Like, this code doesn't convince me of that. This code, however, convinces me that we pass over the whole tree once. Is it right? I don't know. We would have to test it, but we could quickly just do, we could do that with our sum implementation because we have foldable. So we could do, we have simple tree as well. So spago REPL. Not exactly sure why it needs to compile all this twice. Maybe there's more stuff that is necessary. So anyway, type sum import main. Okay. So we should be able to sum simple tree, and we get 117, which I think was the right answer. I'm not going to go all the way back there, but I'm pretty sure that that was the right answer. Oh, it's right here. Nice. We don't care whether it's left or right. It would just change like a very small amount of the code, but I'm pretty sure that my implementation is correct. So I'm certain that my fold map implementation is correct. So we can just do fold R plus 0 simple tree. Import data foldable. And so it's kind of unfair to, like, this isn't the best of tests, but it's an okay test, I think. And the other thing is we're not going through list first. So, which is kind of weird. Also, I'm pretty sure that we can just write to list like this. Import data list. This is not quite right. We can't quite write like this. We would have to write a better function because it's not a cons operator. We're going to end with a bunch of nodes that need to be like put into lists and then concatenated. So I think that this would be I don't know what this would be. I think it would be easier to write the recursive definition. So anyway, it would be much easier to write the recursive definition. In fact, it's up here. Yeah, it's just fold map. Hey, Sky Bro. Oh, MX say hello. I hate it so much. What's going on? No, it's fine. Okay, it doesn't know which version to pick. So what do we want out of this? We want a list of int. What is list A, list A, list A? What is this function called? Oh, it did search. Just being a doofus. Union. No. Append. Emo 8. What's in here? Snack. We need concat at the end, but you can't The only option is to use the semigroup operator. Wait, it doesn't know what fold map is? Didn't I import that? Unexpected token? Oh, probably because I'm putting like weird stuff in here that it doesn't understand. This is trying to combine the it's not gonna work either. Um, right, because it's a monoid. We just need to turn it into a monoid. So there you go. I'm being a doofus. I don't need. I already have fold map will turn it into a monoid. I just need to turn it into a list, which is singleton. There we go. That's what I'm looking for. And then if we wanted to do this with fold R, I really should spend some time to see if I can understand comonads. Yeah. I love the term doofus. It's one of my favorites. Okay, so if we have a fold R, then we need to do this, and nil. Yeah, perfect. It's just a definition like semigroup. Okay, that's how I should think about it, and I should spend the time doing that. And then if we want to fold L, I wish I could use my home key. Right, the accumulator is on the right side now, so we're gonna have, sorry, the accumulator, the X. We need to take. I can't use my delete key. That's great. So accumulator singleton X. And then that should be backwards. Perfect. So what is this? So this is actually, why does this work? I'm kind of surprised that this works. So we have singleton will get applied. We got to flip this. So it's X first. Is anyone else kind of surprised that this works? I think it's one of those things that I just like don't realize what the type is offhand. Anyway, that's pretty cool. So we got, once we have Foldable, we get these things for free, which is really nice. Yes, this will be the definition of fold map. I'm surprised that this composition works is really what I'm trying to say. Because, so, because you have like a type that's like, right, you have your accumulator, It's fold R. So you have your A, your accumulator type, and then you're gonna get like a B or whatever. Uh, so singleton consumes the A. The singleton consumes the A, and then the semigroup consumes the B, and then the result of the singleton. That's completely reasonable, Scarborough, because you don't have to think about those things once you like look at them once. You just kind of let your brain do the work. But anyway, I thought that's kind of interesting. I wrote this like instinctually, but wanted like just letting my brain like think about it more. It's like kind of surprising that it works in the first place. But yeah, it does. So that's great. Um, can with fold L, can I just flip this sign? I don't think I can. No, there's like how do we change this? Well, you know what we can do is go to our my brain is smooth and pretty. Okay. Um what is that thing called? Pointfree.io. We want to convert this. So, yeah, we need Blackbird to do it. This one's a little bit trickier. This one's definitely pretty hard for the brain to understand, I feel like. This one's Blackbird, right? I think so. Because you need to consume this first with the singleton, which is why you need to do that. So first you partially apply this to ACK, and then you come yeah, you consume this, and then you dot it with singleton to get this, and then you stick them together. Yep. It's a trap. Hey, Peanut. Yeah, well, anyway, nobody would write this. Nobody would write this. We're just thinking about it. So don't write this code in production, please. Never, ever do this. Just write this. It's perfectly pointless.io. Nice. Um, this particular one I think is pointless. We shouldn't do this. It's more for fun. Okay, cool. So no one. Yeah, I'm sure this. I am 100% sure this exists in somebody's code base today, and we should probably try to find it. That could be a fun thing to do, maybe. I think that you could search. I mean, I've used Blackbird before, but never in production, like in my daily coding life. I've used it because chat was like, it was probably both of you were like, oh, just try to write that point free. And then I did. And it was probably really difficult. I think that was like the first 6 months of my streaming career was just, hey, can you write that in point free notation from chat? I feel like. Actually, it was super fun to do that stuff. So anyway, all right, that won't be part of the video, luckily. And then next time we'll talk about functors. Functors are amazing.